Hey everyone, welcome back to my session. Let's continue our learning for the Databricks certification for the Spark developer. So as of now, we have completed the intro and the uh, some other coding features of Apache Spark, and now the next session is all about the streaming and analytics with Databricks. So let's analyze with Spark. So let's continue that. Yeah. Okay, so these first two are the course intro and the rest of the details, and let's continue with the actual streaming process. So, introduction to streaming. Let's start it. Yeah. So, okay. So, course overview, and from third slide onwards, it has stream processing information. As as you already aware, like the continuous data flow for those system like banking and risk. Somewhere in those cases the data will flow continuously step by step, and for those things we need to process them at the same time itself, which without any delay. So those things can be handled in the streaming process of Spark. So a stream is an unbound data set, so it has no theoretical beginning nor the end. So the contrast to the batch, which is of known size at the time the processing. Stream can be messages from a messaging system like Kafka or any other stream. Stream can be anything event driven, each as files being processed in real time as they arrive. So for example, the stream you need to process them, you need to provide the result, something like that. So let's streaming let's continue with this, and Spark streaming background. So yeah, from D streams to structured streaming. Initially it was D streams, and then it has become a structured streaming. So Spark streaming was introduced in 2013 as an extension to the core Spark, built on a RDD API using the D stream, means discrete streams model, processing data in small time-based RDD batches. Okay, structured streaming was introduced in 2016, built on DataFrame dataset API, introduced event time processing, simplified API with the SQL-like operations, better handling of late and out of order data. So this handling additionally added to this, and so it is structured streaming now. Micro batching, like for a certain point of time, take the corresponding records and it will process them end to end. It will perform all type of operations, depends on some conditions, and that operations performed based on the conditions to provide better results. So stream processing distributed environment. Okay, micro batches process stream as a series of small batches. Data is calculated into time based chunks. Each chunk processed that as a mini batch job. Mm, Typical batch arrives 100 milliseconds to few seconds. So this is the process flow, just as an example it has given. So next is streaming in real world. Streaming use cases: fraud detection, live dashboards, anomaly detection, mm, clickstream analysis, clickstream analysis, and sensor and IoT of Internet of Things monitoring, data ingestion and transformations. So all the other stuff. Common sources is Kafka, Kinesis, Event Hub, some alert and notifications mechanism, Lakehouse like Delta Lake and Iceberg will help you to get that type of data. Let's go back to the next slide. Show. So it explains exclusively the structured streaming part. Let's go to the third slide. Okay. Introduction to structured streaming. That was the basic given. Now the detailed information about the structured streaming is given. So declarative API for distributed stream processing. Structured streaming treats streaming as a raw applied to the table, appended to the table. Same data frame API as batch processing. Nothing new as batch processing, but automatic optimization of query plans. Okay, watermark support for late data, end to end is exactly once guarantee. So this is the main event times. It's time based. In a particular time window, it will process and it will wait for using watermark for a certain time, and after that, it will process them. Apart from that, streaming sources and sinks. Sources is like built-in sources like files or Kafka sockets or RAID, something like that. These are the streaming sources, and sinks also the same files Kafka for each console, or any memory. The that is a sink actually. That is the destination. This is a source and this is a destination. Autoloader cloud files is Databricks source for high performance cloud storage ingestion with auto schema handling. So Databricks built something like called autoloader. It will help you to do ingestions, continuous ingestion of the files. So structured streaming connects to sources, so and so, and sinks. Sinks. Okay, files and Kafka are common for both input and output. Uh, the for each sync lets you apply custom logic such as writing to database. Okay, console and memory sinks are mainly for debugging. For each, for the DB, console and memory sinks are debugging. Databricks autoloader source uses cloud file automatically tracks new files in cloud storage and supports schema changes, make it handy for evaluating the ETL tasks. Yeah, sorry for the delay. Yeah. So let's go through the structured streaming part. Data stream reader and data stream writer. These are the two operations which will help you to read and write from stream reader. Stream writer we will call usually. So create streaming data frames, accessed through Spark session read stream. So if you see the code df spark dot read stream, format is Kafka option. If there is any specific host information, and the multiple options you can give depends on the configuration variables you want, and config also you can add here, and if there's any configuration changes need to be done. Okay, stream writer, write on a so and so and in a different mode, and read is like considered as a load here in this case. So whatever the data comes at that point of time, it will read and it will try to process that. So yeah, same as batch read and write the similar way. The syntax also is almost similar, like format here is a Kafka and format here is Kafka. Read, instead of read, you'll use read stream here, and instead of write you'll use write stream here, and start option will be there. Here it is load. Streaming transformations. Read stream option, format delta load your input path. Okay, and here build stream data frame. It's a building of data frame read stream, same spark dot read stream. The same way the data frame building option so and so, and format is in what type of data. Delta is a delta table like in the Databricks environment. Any other type of format like in a also we can do it. Uh, Apply some transformations here like df dot filter column so and so equals to email. Perform data frame transformations as you would normal data frame. Any data frame, the same way we'll do some column operations and filter operations. It's the same way we also doing the same um, in this as well. Streaming queries like so if you observe this like write stream query result. So email query email traffic df here write stream. Output mode is append. Format is delta. Query name so and so query name. Email traffic and trigger process time 1 second means every 1 second it will try to process like start a streaming query with options. This will run indefinitely means every 1 minute it will keep on checking whatever the data is available it try to process. Checkpoint location you need to give to recovery purpose. At any point of time if this is failed and it needs to start from that particular failure point. Okay, and you want to stop stream, then you can stop the streaming. Wait for termination like await termination is the um, these two are used to stop the stream. Trigger triggers are the one like start the stream is the trigger mainly, and what interval you need to start. Different type of intervals will be there to start. One is default trigger as soon as possible, process data as soon as the previous micro batch completes. So start if you give like x number of records reads complete, and it will trigger again if there is any number of records will there, and take that and it will read stream and start again. Or else in a specific interval every 2 minutes you need to specify, then yeah, fixed interval like every 2 minutes it needs to start. Process data at specified time intervals. Useful for controlling resource usage like every 2 minutes, every 5 minutes, something like that you can do that. And available new trigger available new trigger available now trigger. Available now trigger is like process available data then stops. Okay, won't wait for more new data to arrive afterwards. So once it is done, only one time triggers. One time triggers like available now trigger. So one time processing for available data, that is process batches at fixed intervals. Default with no trigger is specified. That is automatically it will start and it will continue. Okay. So triggers control when and how often Spark processes new data in a structured streaming job. Mention the trade-off between legacy and throughput that is controlled by triggers. Output modes are like append, update, and complete. Append is the default mode. Um, Append is the default mode. Only adds new records to the sync. Best for sample uh, stateless queries without aggregations. So that is append. Update is aggregations related. Okay, ideal for dashboards and real-time metrics. See, keep on updating, modify existing records and adds new ones. Only output records that are changed since last trigger. Okay, complete means ideal for running totals like leaderboards. Like entire thing needs to be shown in that. Board. So in those cases we'll use complete, like it will just wipe out everything and it'll like it will create a new enters the result total and total table to a sync each time. So requires some aggregations. Okay, so this is okay. Monitoring stream queries like for example if you want to monitor something in a stream, okay, there are monitoring areas in Spark UI. Understanding your streaming application's health. Monitoring via Spark UI. Stream tab shows active queries, progress details per batch. Check if Data frame is streaming. DF is streaming. We need to check. Get unique identifier. Streaming query.id. Streaming query.status. Status of that particular thing. Monitor streaming query progress. Last progress. So ID status last progress. There will be a unique identifier each streaming query. So for that, I think you need to get an ID. So that ID will be displayed by dot ID, status, and last progress. Okay, some useful information. Yeah, this is good. Use external monitoring tools like Datadog, Grafana, Prometheus, etc. Monitor performance, monitor processing rates and latency, memory usage, and garbage collection. So some useful in inspection functions. Okay. This is the way. Okay, this is done. Let's go back to the next slide session. It's a video like how to use structured streaming with the help of Databricks environment. That's what it's gonna show. So we are not gonna go through those videos. Like if you want to see in a quick reference, I'm just gonna show up. That's it. So next, advanced stream processing. Let's continue with this, and let's go back. Okay, slide 3. Okay, stateful versus stateless operation. State is pretty important here in this streaming process. State itself decides like where the process is currently at and what needs to be done, what exactly done in the past. So understand how streaming operations handle data over time. Stateless operations process each record independently, no memory of previous records. Select these kind of operations like narrow transformations are here stateless, wide transformations are here stateful. Okay, so narrow transformations, these are narrow transformations. Maintain information across batches, requires checkpoint location. Yeah, from where it needs to restart again. Example, group by, join, deduplicates. These are the main operations. Window operations um, are the main things in this. So let's continue. Maintain state. Okay, state maintaining is how crucial by explaining. We'll be explaining about this business driver, worker, and all the corresponding DBs and checkpoint directory will be there. Okay, managing state in distributed streaming applications like challenges in distributed state. Okay, data is distributed across worker nodes. Need fault tolerance for state recovery. Yeah, memory limitations for large state, consistency across node failures. RocksDB as state backend, built-in built-in state store for Spark structured streaming. RocksDB is the built-in state store for structured Spark structured streaming. Provides persistence with high performance. Features is efficient storage and retrieval, automatic compassion, support for large state sizes. Okay. Key takeaway: Spark abstracts away much of the complexity of managing state, but understanding how state is stored and recovered in is crucial for tuning performance and ensure fault tolerance. So every state will be stored. That is a rocks DB that will help you to store the state of that particular checkpoint. And if there is any fault tolerance, like failure, recovery, all those other stuff will be happen using this. Stream join, it's very important concept. Like stream join is depends on the join and the corresponding time frames and when it needs to wait for a particular record and perform the joining operation. All the other stuff will be taken care under this. uh, there are two types, static and streaming. So for example, if you are reading from a static source and you're writing to a streaming frame, it's a static stream. uh, type of operation. And stream join will be there, like both are streaming, like from the input, whatever you're reading is also from a stream process, and writing is also from a stream process. Then in those cases we'll use different perspectives. So now a streaming data frame can be joined with another streaming data frame, a static data frame including a normal data frame, or are results of a complete output mode streaming operation. So once it is completed, it is static only. So that static, if you read and if you do something, that's also considered as static. Okay, all join types supported except full and cross. Okay, stream join are not support full and cross. Challenges and limitations. Joins require maintaining state, increasing memory usage. Event from both streams must be within a definite defined interval. Late arriving data can present challenges. So this is the main drawbacks you have. Supports inner, left outer, left semi, right anti, left anti. Okay, streaming aggregations. Let's see. Types of streaming aggregations typically count sum, average, min, max. All those things can be performed. Approximate functions are available which typically perform better. Approx count distinct. How can we aggregate an incomplete data set? Recall that streaming data frame are unbound data sets. Yeah, the answer is to aggregate based upon windows. So you need to define a window. In that specific window only, you need to wait for that particular window strategy. And once it is the 10 minutes or whatever the minutes you specified in the window, it will be considered. And whatever the records that are coming in through that particular time frame, it will perform the operation. What is this approx count distinct? Approximate functions are available which typically perform better. Instead of count, approx count. Instead of average, approx average. Maybe with you using that, it can be performed better, which is approx count distinct. Okay, fine. So how window operations will work, like tumbling window, sliding window, session windows, like understanding window streaming computation, like tumbling window, like fixed non-overlapping intervals. Like for example, window this much to this much, window 2 is this much to this much. How many events are coming and it will perform. So some sliding window is like there is a combination of both together, like overlapping windows, uh, where an event can belong to multiple windows. Like for example, this area, this event is between like 1 and 2, so that is a sliding window. Session window, one session starts and it will performs and there will be some gap, and after that another session starts. Dynamically sized windows based on user activity with gaps or session timeouts. There will be a session timeout in between that session timeout. So these are the three types of window operations here. Okay, aggregating over a streaming is only meaningful if we define boundaries in time. Tumbling and sliding are time based, while session window are activity based. Session window are activity based, time based, and activity. Okay. Next, get the number of CC authorizations for the last 60 seconds over 30 every 30 seconds. Okay, 60 seconds is the window duration, and slide duration is 30 seconds. So yeah, import into count authorizations, so and so schema information, and after that window authorizations is authorizations dot group by window. It will start time column, authorizations dot timestamp, window duration 60 seconds, slide duration 30 seconds. Each window covers the last 60 seconds. New window starts every 30 seconds. Authorization card ID aggregations will happen on top of that. Grouping by card ID, of course. Counting transactions per window. Each transactions per window it will cover. This example shows a sliding window operation in streaming where we count the number of credit card authorizations in the last 60 seconds. Okay, this is good. Mm. Handling late arriving data using watermark, of course. Watermark will be 2 minutes, and what happens is even the window started at for 60 seconds and it will wait for that missing times. Okay, event can be delayed in arriving for many reasons. Okay, defining how long Spark waits for out of order events. That is the watermark. It will define timestamp and so. Allow late events up to 2 minutes. So even the late event come within that 2 minutes range after the completion of the 60 seconds window, it will consider that and it will performs that operation. Okay. Watermark tells Spark how long to wait for late data before finalizing a window. That closing of the window, it will wait and it will do the trade-off using that. A longer watermark increases correctness but may use more memory and delay results. Shorter watermark improves speed but risk dropping late events. So optimal value depends on the situation on the watermarking will be necessary. Okay, this is done. Let's go back. And this is the video demo. And yes, this is completed. Let's restart the test here. Restart the test. I'm taking a live test here. I think I scored good percentage, but let's see. Now, how will I score? Okay. So in the sliding window implementation with a 3 minute window duration and 1 minute sliding interval, what is the key architectural consideration for managing overlapping window computations and their impact resource utilization? Each sliding interval create okay. Overlapping windows are automatically merged to reduce computational complexity. No, they won't be merged. Sliding windows automatically optimize memory usage by sharing computations between overlapping window. Each sliding interval creates overlapping windows that requires maintaining state of multiple concurrent windows. Each record potentially contributes to multiple window calculations, increasing computational and memory overhead compared to tumbling window. Let's see this. Sliding window eliminates the need for watermark. No. Which of the following built-in stream sinks is specifically used for interactive querying and debugging results? Console and memory sinks for testing and debugging. Kafka sync, file sync directory output topic and runs for each. For a streaming query designed to maintain on ongoing computation, such as a running total count of all records received or a leaderboard of suggested metrics. Complete. Which output mode is better? So complete, right? Leaderboard means overall information it needs, and count totals are running all records. So complete. In the context of streaming query monitoring and lifecycle management, what is the significance of properly stopping active streaming queries before starting new one with the same query name? Stop existing queries with the same name, prevent resource conflicts, checkpoint corruption, and ensures proper cleanup of streaming state, as multiple queries with identical names can interface with each other's checkpoint location and state management. This is correct. If you do with the same name, it the entire mechanism of this thing is depends on the name, application name or some name. So that name should not be separate. That should not be unique. Okay, that should be unique. So that's the way we can. In the context of streaming data frame operations, what is the fundamental distinction between stateful and stateless transformations, and why is this important for distributed stream processing? Stateful operations can only be performed on the driver node, while stateless operations distributed across executors. No. Stateless operations require explicit schema definition, while stateful operations no, both need schema definition. It's nothing dependent to schema actually. Stateful operations require more memory, while stateless operations provide better performance. Stateless transformations, this may be good, but let's see. Select with the column operates on individual records without maintaining state across batches, while stateful operations like aggregations and joins requires maintaining state across multiple cross batches, impacting scalability and fault tolerance. Of course, this is correct. When configuring stream joins with watermarks and event time constraints, what is the primary architectural benefit that enables full state cleanup? Long running streaming applications. Watermark combined with event time contains allowed structured streaming determine when join state can be safely removed. Watermarks automatically optimize join. No, join algorithms cannot be optimized with watermark. Event time constraints eliminate the need of checkpointing in streaming joins. It won't eliminate, both are different. Event time constraints automatically partition data across multiple clusters for better performance. Watermarks combined with event time constraints allow structured streaming to determine when joint state is safely moved, preventing unbounded state growth by defining time boundaries for how long to retain state for potential matches. That's correct. Which method is used to properly stop a streaming query and wait for the final batch to complete processing? This is a good question. Query terminate? No. This may go wrong, but let's try. Structured streaming replaced the older D stream model. What key technical capability did structured streaming introduce that D streams lacked, enabling improved fault tolerance and consistency for time-based data? Event time sliding window. Okay, 1 minute. Mandatory use of Kafka sync all output no. Ability to process streams using legacy no. Event time processing and better handling of late and out of order data. This is correct. Structured streaming treats data as a infinite table and provides end-to-end exactly once guarantee, which mandatory configuration option typically specified in the write stream operation is essential to enable fault tolerance and maintaining the state management across batches. Checkpointing is the basic thing. Okay, in stateful stream processing, watermarks are crucial for managing state size and ensure correctness when dealing with out of order events. What is the technical definition of a watermark? A definition to how long Spark will wait for late arriving events before considering a window or state complete and cleanup of the considering state corresponding state. Continuous function that automatically optimizes the underlying parquet files. No required metadata column that records the time and the record was processed by the cluster. The mechanism of force new micro batch. No, this is not next. This is correct. What characteristic makes transformations like select and filter fundamentally simpler to execute in structured streaming compared to group by join? Stateless, those are. They are stateless operations, process each record independently without memory of a previous batch, of course. This is correct. When implementing triggers in Spark structured streaming, what is the fundamental difference between using processing time triggers versus available now triggers for controlling micro batches? Available now, processing time triggers executes micro batches at regular time intervals, 10 seconds, while available now triggers process all available data in a single batch and then stops. This is correct. In Spark structured streaming, what is the fundamental architectural difference between tumbling and sliding windows, and how does this impact state management in streaming? Tumbling windows are fixed, non overlapping time intervals, while sliding windows overlap by moving a regular interval smaller than the window duration, requiring more complex state management due to overlapping competitions. Yeah, that's correct. In Spark structured streaming output modes, what is the critical using append mode with windowed aggregations that have watermarks? In append mode with watermarks, aggregates can only be produced once and cannot be updated, allowing the engine to delete the aggregate state once finalized, which keeps overall aggregation state bounded but in slate data beyond watermark discharge. Okay, this is correct. Structured streaming support joining two streaming data frames, but this operation has limitations due to the state maintenance complexity, which two fundamental SQL join types are explicitly not supported to stream joins, full and cross, full outer and cross. When working with streaming data frames and schema definition, what is the primary advantage of complexity defining schemas compared to relying on schema inference in production streaming application? Always try to define schema. Explicit schema definition ensures consistent data type across distributed partitions, avoids costly schema inference operations on the each micro batch. This is correct. In the core technical difference between stateless operations and stateful operations, what is the okay? Stateless operations use event time processing while stateful operations use processing time. No, stateless operations can maintain information across processing batches, while stateless operations do not. This is correct. Which statement about stateful operations in Spark structured streaming is true? They process each record independently. No. They don't require checkpoint location. No. They never need watermarks. No. They maintain state across mission batches. This is correct. Micro batching is the technical basis of distributed stream processing in Spark. What specifically defines a micro batch chunk, allowing it to be processed as a mini batch job in a distributed environment. A chunk is defined by a fixed predetermined number of records. No. A chunk is defined by a underlying cloud storage file size. No. A chunk only contains record that failed schema evaluation. No. The chunk is collected into time based intervals. This is correct. When implementing watermarks in Spark distributed streaming for late data handling, what is the critical architecture principle that determines when an aggregation state can be safely cleaned up? Watermark. Come on, watermark defines how long to wait for late events. Once done, once done with the watermark passes the window end time, the engine can finalize the aggregate and clean up the state. Let's see what one question that is wrong. What is that? That I know. Query terminate query stop and query wait terminate. This is what it is. Which method is used to properly stop a streaming query and wait for the final batch to complete processing? Query terminate, query stop, and query wait it. Query wait termination. Okay, this is the wrong answer. Remaining all are correct. It's very good. Okay. So yeah, this is the end of our session. Yeah, let's continue with the next session. And thanks for watching. And please try to subscribe.